Hiya. So the last section that we have for today in our videos is we're going to be talking about fluctuations, as in when we have our normal approximation, how close or so how close to reality is this approximation kind of going to give us? And so basically the idea of a fluctuation is that we're going to start with n, and we're going to just increase it. So we're just going to keep increasing our n and n and n, and it's going to go, 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 go. So we're just doing a trial over and over and over and over and over and over. So if you think about this, the more times we do a trial, the more accurate information we're going to get, right? And so what we would expect from this is that, so normally when we get a curve, right, we normally get something like this. Maybe I should do this in black. We would get something like, let me fix this. Bloop. Can this not erase? Nope, because I need to be here. Cool. So normally we get a curve like this, right? And as we get more and more information, we get more and more numbers, we're going to kind of go closer and closer to the expected value, right? So we would expect kind of something like this as we get higher and higher n. So this is small n, and this is big N. And so this is basically the idea that we're going to get when it comes to fluctuations. And what you're going to see here is if you look at, if I did this right, if we look at the mean value, close enough. Let's get that as the mean value. Let me see if I can redo this. There. If we get the mean value here, what you're going to notice is my standard deviation is going to be different between the two, right? So if I look at, so remember if we look at one standard deviation, we're going to want roughly 68% to be inside of it. So in this case, it's going to be something like here is going to be our standard deviation. Obviously, it's not perfect because I drew it by hand, but bear with me. In this other one, what we're going to notice is our standard deviation is going to be much, much closer, right? So notice how the standard deviation kind of is significantly further in. And the reason for this, so we're going to kind of look at the reasoning behind this. We're going to look at some numbers, and then we're going to give a few theorems that kind of state this in a more concrete sense. So you can kind of see that the size of the fluctuations, how far or wide something gets, is going to be dependent on our sigma. So the size of our sigma is going to be the size of our fluctuation. And so let's kind of look at this. So the typical size of a random fluctuation, so if we look at the relative frequency of successes, this is going to be the size of sigma divided by the number of iterations we have. So in other words, what we have is something like this. We have our sigma on top. This is our sigma. And we divide by the number of iterations we have. And so if I take this n, so this is basically square root of n squared, and these n's kind of cancel inside, and I end up with this equation here. And so we're going to look at this and let's see kind of what happens if we try to maximize this. So if I look at this inner part, we have p times 1 minus p. So if I look at p times 1 minus p, what you're going to notice is when p is equal to 1/2, we have 1/2 times 1/2, which is 1/4. But anything else than this is always going to be less than 1/4. Like, for example, if I take 1/3 times 2/3, here I get 2/9, which is obviously less than 1/4. And you can kind of see that no matter what I choose, I'm going to get something smaller. And the kind of easy way to see this is if I have 1 over n and 1 minus 1 over n, we get n minus 1 over n squared. And so you can very quickly see that, this equal, that one, well, not quickly, but like the idea here behind this is that we're going to be limited by this 1/4. So what I'm going to do is, since we're limited by this 1/4, I'm just going to replace this p times 1 over p by 1/4, right? So I have less than or equal to 1 over, this becomes the square root of 4, right? So I can kind of think of the square root all the way over, but since this one on top is basically nothing, I can just remove that. And then I can take this 4 out, and we get 1 over 2 to the square root of n. So this is kind of how our fluctuations are kind of working. So in other words, as our n gets bigger, you're going to see this 1 over square root of n part is going to go to 0. In other words, this sigma is going to get smaller and smaller and smaller and smaller. It's going to go closer to nothingness. And this is exactly what the square root law is kind of saying. So let's look at the square root law. It's going to be saying two different things at once. So square root law, it's saying if we have n independent trials, so we have n independent trials, and n has to be sufficiently large, and p is the probability of success, then we have two different points. The first point is that the number of successes with high probability is going to lie in a relatively small interval of numbers, which is going to be centered around mu, which is our expected value, and with a width which is a moderate multiple of square root of n. Now this multiple of square root of n is really coming from the standard deviation. So if you think about this, if you look at the values, themselves, then what's happening is, so say if my value here is x, then as my thing gets smaller, I'm going to have more and more, I guess I should, yeah. This is not a good way to kind of do this. So like say if I have something small. So say I have, I guess it'll be a histogram in the beginning. So if I have something like this, where I have 1, 2, 3, 1, 2, 3, 4, 5, for example. So I do 1, 2, 3, 4, 5, 6, 7, 8, 9 trials, and this is the distribution I get. As I increase n, then what'll happen is potentially I'll get something a little different. So I'll basically like say we double everything. So I'd get 1 here, we'd get 4 here, and we'd get 9 here. 4, 1. So here we have 9, 4, 1. So you can kind of see as I do more and more, we're going to get a larger concentration of numbers in this center part. And this is what this first part is saying. The number of successes is going to go towards the expected value. Here the expected value we're going to say is equal to 3. Now the proportion, so that's where this number of successes is coming from. And it's saying basically our square root of n is going to be on this side, right? So we can either look on either side of this. The other thing that we can look at is the proportion of successes. And this is really where this kind of graph comes in, because this is looking at the the proportion of them, right? So here we have, so say roughly 1/3 are here, and this one will become like 1/6 or something. So this is really trying to see how many of these things end up in this area. And what it turns out to be is the proportion is again going to lie on a small interval which is centered on p. So in this case, it's really going to be whatever the probability is. This is where the proportion of success is going to be. Actually, so this is closer to the number of successes, right? So this is how we're kind of dividing this, right? And then the probability, the proportion of successes, which is how often something will occur, this is where we were getting this divide by n thing. So, right, the relative frequency gives us this square root of p times 1 minus p divided by n. I wish I had a laser, but anyway. And so this is going to lie on a small interval which is centered on p. So in other words, the probability p is going to be the most often seen. And then everything else is going to be 1 over square root of n. So that kind of gives us how these things are working, whether it's the proportion or the number of successes. And this law is basically coming to us called the square root law. Now, the square root law is pretty nice, but it actually implies something even cooler. And this is called the law of large numbers. So let me go over the law of large numbers, because this is, to be fair, one of my... I guess I should have scrolled up a little. This is one of my favorite theorems in mathematics, especially probability theory, to be fair. And what this is saying is we start off with n different trials. So we let n be the number of trials, of independent trials, and we're going to let n be large. We let p be the probability of success. So we just let p as always, and we're going to take some epsilon, which is bigger than 0. So here you should be thinking, oh no, not epsilon delta proofs. Don't worry, we're not doing any proofs like calculus. We're just using the same notation to get that same idea. Epsilon can be really, really small. And what we're going to do is we're going to say that p, the proportion of successes in n trials, differs from p by less than epsilon. So remember this proportion from before. The proportion of successes is a moderate multiple of 1 over n. So in other words, normally we have p times 1 over square root of n. And here we're saying that the difference is less than epsilon. With a width of, sorry. So it's p plus or minus 1 over square root of n. And so what we're saying here is this epsilon is going to be less than, is it less than? It's going to be roughly like 1 over square root of n, right? This is kind of where we're going with this idea. And as this gets bigger and bigger, this is going to go to 1. So basically what you can kind of think about this as n goes to infinity. What this is basically saying is that the more trials we conduct, the closer to p our relative frequency will become. So in other words, the more we test something, so we're testing things out randomly, we don't actually know the probability, then as we test things out, then the probability that we see is going to get closer and closer to the actual probability. This width is going to get smaller and smaller until we find exactly what that probability is. Now, this entire idea is called the law of large numbers. It's a really cool concept. This particular version, the way we're seeing it, is actually technically called the strong law of large numbers. There's a weak law of large numbers as well, which is slightly weaker than this. But it's a really cool idea. And so, yeah, so this video is long enough. It's the last video for the day. So thank you for following. I will see you next week for the continuation of the content. Have a good week. Bye.